Hi everyone, I'm Jason Morgan, Content Director for Fleet Equipment, and welcome to Fleet Equipment Unscripted. Today we're talking with Suman Narayanan, Director of Engineering at Daimler Truck North America. Suman, great to see you. You look great. I appreciate you taking the time.
Thank you, Jason. Thanks for having me on your program.
For sure. So I'm really excited to talk to you about autonomous technology. And I know we're going to get to kind of a virtual walk around of a autonomous chassis here, but let's just lay some groundwork. Had a really great conversation with Joanna Butler and Peter von Schmidt here earlier this year about autonomous technology. And I think what hit me most was that I've seen the technology before. It does work great, but the business case of it is really coming together in terms of providing the chassis to the different companies that you do, the service support that's going behind it, the virtual driver development, all that good stuff. So I'm really excited to talk to you about the redundancy that goes into the chassis and those differences. So if you could just kind of kick us off here, and just what are the requirements for redundancy in an autonomous chassis, an autonomous operation?
Thank you, Jason. Thanks for showing interest in the program that we are doing here at Daimler Truck North America. We are committed to highway safety and freight efficiency. And I'm standing in front of one of our redundant vehicle platforms. So Autonomous Cascadia's foundation requires a vehicle that can operate without a human driver behind its wheels at the time. So what does it mean? Redundancy is a term that is used heavily in the industry, but let's break it down to what it actually entails.
Right.
Today, when a human driver is operating a Class 8 vehicle, should there be an electrical failure, should there be an electronic failure in the braking system, for instance, the driver gets the pneumatic backup available for him or her to control the vehicle and bring it to a safe state.
Oh, okay.
Now, when we imagine an autonomous Cascadia where there is no human behind the wheels, we need to start thinking about all the activities and all the steps that a human driver takes today. And that entails the term redundancy.
Right. So in this case, like there aren't two braking systems on the truck. There's not two drums. There's not two disc brakes. It's redundancy in the activation and electrical system of that. Is that correct, or are there two systems in that example?
That is correct. There are not two redundant brake calipers. There are not two redundant brake disc brake systems. However, the redundancy in the braking system is handled in such a way that should there be any electrical or electronic failure in the primary brake system, we have a secondary brake system that performs all the activities that are available for a human driver today. The secondary brake system is able to achieve all the deceleration commands coming from a self-driving system so that the vehicle can be controlled safely even when there is a primary brake system failure.
When you talk about it, it's like a redundant braking system. I'm thinking, are we doubling braking components? Are there double brake brake pads on there? But a lot of the electronic control. I know that one of the things on the Cascadia chassis that you're delivering to your autonomous partners, there's more than, I think it's 1,500 added features or different tweaks that you have to make to that chassis to deliver it to your autonomous partners. Is that right? And can you give me kind of an example of, I mean, you gave me the brake one there, but what other changes go into this?
Absolutely. We jumped right into the braking system as an easy example for us to understand what is so unique or different about this vehicle. But let's take one step backward. Braking system is one of the key systems that must have redundancy because we are trying to operate the vehicle without a human driver behind the controls. But what about steering system? If you think about it, the primary role of a driver goes beyond just controlling the vehicle in the lateral and longitudinal direction. But those are very key elements for safety. So we have redundancy in terms of braking system, and also we have redundancy in terms of steering system. Under the hood, you can see our steering system and steering controller. What you see here is an adaptive power steering with two servo motors. And these two servo motors are able to faithfully fulfill any requests coming from the self-driving system so that the vehicle can be controlled in the lateral direction. Just like in the braking system, we also have redundancy in the steering system. These two servo motors are capable independently of providing up to 8 Newton-meter torque. And should there be any problem or any electronic fault with one of the servo motors, the other servo motor is able to take over and provide the lateral control that is needed to keep the vehicle on a safe trajectory. And in addition to braking and steering, which are two important controllers for the controllability of the vehicle, we also are introducing electronic park brake in this vehicle. As you can imagine, if there is any failure in the electronic park brake system, we also make sure that the redundancy or the fail operational attributes of the electronic park brake system is invoked so that the vehicle can be safely parked and operated. There are two other systems that also have redundancy. It's hard to see, but I would like to show you one of those elements. It's the low voltage power net. As you can imagine, some of these controllers, such as the brakes, the steering, and other critical components of a self-driving system, they all cannot afford to have a loss in low voltage power, or they cannot afford to have a loss in electronic and electrical communication. So in addition to redundancy in brakes, in addition to redundancy in steering system and electronic park brake system, we also have redundancy in low voltage power, and we have redundancy in electronic communication between the controllers. This ensures that all controllers are always having low voltage power, and they also have electronic communication available to them. And when I say low voltage, the entire truck is still in a 12-volt architecture, and that is important to know because all trucks in North America have the 12-volt architecture as standard, and the truck behind us, the self-driving truck that we are developing together with Torque Robotics and Waymo, will be in a 12-volt architecture. Early on in this project, very quickly we realized that in order to fulfill all the electrical and electronic requirements of the base vehicle, plus the increased demand coming from the self-driving system, we needed to rethink our low voltage power supply strategy. We evaluated several options, and we believe we have one of the best options out there, not just for manufacturability and serviceability, but also for the most robust functionality of our low voltage power supply. We are developing a 48-volt generator solution, which means that the power is generated at 48 volts. However, we immediately step it down to 12 volts and branch it into 3 high-integrity low-voltage buses or 3 high-integrity low-voltage connections within the vehicle. The purpose of us doing that is to make sure that we generate an adequate capacity, which is later on distributed evenly to the vehicle, and the vehicle still remains in a 12-volt architecture, which is very important for us and our customers so that the service industry and our technicians in the field can operate on these vehicles just as they would operate on a standard Cascadia.
Right, for sure. Again, sorry, another basic question, just so I understand too. Does that mean more batteries on the battery pack? Are you able to do that with am I adding batteries to the truck now in that regard? Are you able to do this with what's already there?
So we talked about the generation. So we are generating at higher capacity so that we can fulfill the higher demand.
Yeah.
But what about a scenario where the alternator fails while in the middle of a mission? Today, a human driver depends on the stored energy or the stored power in the vehicle in order to come to a safe state. Because once the belt drive snaps, there is no way of generating more low voltage power in the vehicle. A similar situation can also happen when it is on an autonomous mission. Anticipating that, we have equipped the autonomous ready Cascadia with additional batteries, 50% more batteries as a standard Cascadia, as you can imagine.
Interesting.
A standard Cascadia has 2 sets of 4 batteries, so totaling to 8 batteries. The autonomous ready Cascadia that you see behind us has 12 sets of batteries. What it does, it provides additional stored voltage even in case of a catastrophic failure in an alternator or the belt drive, ensuring that the vehicle can come to a safe state and send any distress signals and wait for support.
Okay, lots of great redundancy examples. Is there anything new or additional in those 1,500 requirements or chassis innovations that you put on there that you're delivering as well?
Absolutely. If you think about the key elements of what makes a vehicle autonomous ready, braking, steering, low voltage power net, and redundancy in electronic architecture are key elements. But it goes beyond just those systems. Think about our engines, transmission, engine brake control, and beyond. Every system that is available for a human driver today, every system that can be controlled by a human driver today, now also needs to be enhanced in such a way that it can respond to the commands coming from a self-driving system. And not only that, any system, whether it is critical or non-critical to the self-driving system, if it has a deterioration in its health state, it should be immediately notified, and the self-driving system has immediate access to the diagnostic trouble codes and other errors in the system. We talked about key systems such as brakes, steering, and we also talked about systems that do not have redundancy, such as powertrain systems. However, we also have However, we also have methodologies that need to be adopted while developing a self-driving system. For example, the self-driving system cannot afford to have a single point of failure. We diligently follow ISO standards. We also want to make sure that the functional safety elements are taken into consideration so that there are no single points of failure when it comes to operating a self-driving system. And we also acknowledge that the self-driving system may be subject to external threat vectors, maybe to someone who wants to hack these vehicles. Cybersecurity is no longer a nice-to-have feature. Cybersecurity is a must-have feature when it comes to self-driving system. Key controllers in our vehicles are enhanced when it comes to their cybersecurity capabilities so that we can not only monitor for any activities, but they also only respond to authorized commands, making these vehicles safe not only from the operational perspective, but also from connected vehicles perspective. Anyone who is serious in operating a self-driving system out in the market must not only ensure that it has the right level of redundancy, but they must also ensure that all the functional safety elements are implemented and make sure that it is bulletproof and ironclad when it comes to cybersecurity features.
Okay, great. Well, I'm excited to see it. Why don't you take us for a walk around the truck?
Here under the hood, you can see our redundant steering system. These are the two servo motors that I was mentioning. These two servo motors are acting in a parallel redundancy fashion, which means that both these servo motors, each of them are capable of up to 8 Newton meters in torque. Both of these servo motors are getting the commands for any steering angle simultaneously, and they're able to fulfill them at the same time, which means that half of the load is taken care by one, while the remaining is taken care by the other. Should there be any fault in one of the motors, or should there be any fault in the electrical or the electronic communication, then immediately the other servo motor takes control of it and brings the vehicle to safety.
In regular operation, they're both being utilized. It's not like a primary system and then a backup system waiting for that first primary system to fail. They are both being utilized in the steering.
Exactly. That is correct. So both these systems are working in parallel. So that is why the term parallel redundancy becomes very important when it comes to steering, because you will see that different when it comes to the braking system, where you have a sequential redundancy. There is a primary brake controller which fulfills at all times, and should that have any challenges, then the secondary system takes control. When it comes to steering, we have a parallel redundancy, which means both servo motors are working at all times. They're just sharing the load, and should one fail, the other one is designed capable of taking control.
What is the reason to go with one or the other? Like, why have parallel in steering and then sequential in braking? What are the options there?
When it comes to steering system, latency becomes extremely important. There is very little room for error. That is why we wanted to make sure that both these systems are working in parallel. Should one have any failure, the other one is able to take control. When it comes to braking system, we have a primary brake controller that is able to fulfill all the requirements coming from a self-driving system. Should it encounter any electrical or electronic issue, the secondary takes over and provides all the required braking functionalities. So that is why we have a difference in terms of a parallel redundancy when it comes to steering system and a sequential redundancy when it comes to brake system.
Right. One quick follow-up on that too. Does the parallel redundancy in steering, does that give you the visibility, but in terms of like a degradation of a part or being alerted that there could be a problem sooner, does that let you have visibility into that rather than it not working and then having to work kind of a thing?
The advantage of parallel redundancy are quite a bit, and in this case what we are having is the redundancy element of it is not compromised due to latency. So for example, if there is a leak or if there is any deterioration in the hydraulic support that the steering system has, we have the capability of detecting it, and we have the capability of providing all the support that is provided by the hydraulic system by just the servo-assisted motors.
Very cool.
If you look at everything upstream of the steering gear and downstream of the steering gear, for example, the eye shaft, the steering column, all the way to the steering wheel, and also downstream, the pitman arm, the linkages that connect the wheels, they are identical to what you would see in a classic Cascadia. The key element that adds redundancy is here, where we have two 8-Newton servo meters that have redundancy in electronic communication, low voltage capabilities, providing the maximum controllability that is needed for a self-driving operation.
Yeah, very cool.
On the other side of the vehicle, you can see the component that provides a 48-volt generation capability. Here, you can see a 48-volt alternator. if you open a hood of a classic Cascadia and look at it, you would have a 12-volt alternator going in the exact same position. We have designed a 48-volt alternator that is able to generate at a higher power while maintaining all the serviceability and the design attributes that are comfortable and familiar for today's service and operation. Once we generate at 48 volts, we are able to bring it down to the back of the vehicle where you can see how we distribute that power. We have 3 DC-DC controllers. These 3 DC-DC controllers step down the voltage from a 48 volt down to a 12 volt system so that the entire vehicle can consume at a 12 volt architecture. We have 3 low voltage buses, and all 3 of them are what we call as high integrity low voltage buses. And we call it a high integrity because we monitor the current and the voltage ripples to make sure that all electronic controllers are getting clean power and voltage at all times. And should there be any interruption or any disturbance or any deterioration, we have insight into that immediately, and we're able to make any corrective measures. Under the fifth wheel, it is hard to see, but I'm going to point right at this area. So here is your fifth wheel, and under the fifth wheel, you would see the primary brake controller. This primary brake controller makes sure that we have all the braking capabilities, such as anti-lock braking system, and also stability requirements such as roll stability and enhanced stability are provided at all times by this primary brake controller, which means that a self-driving system can ask for any kind of deceleration that is required for safe operation, and this system ensures that we have anti-lock braking system capability and also enhanced stability available at all times. If there is any failure in this system, if there is any electronic interruption or electrical interruption, we have the secondary brake system, which is installed right in front of it. So there you see the secondary brake controller, which ensures that all braking requirements such as anti-lock braking and also any kind of stopping distance that is needed to provide maximum stability and safety for the vehicle. Earlier, we had mentioned that we generate at 48 volts and step it down to 12 volts to make sure that the entire vehicle still remains in a 12 volt architecture. But what if there is a sudden loss of power due to an alternator failure? We want to make sure that the vehicle has adequate stored power. As a result, we have enhanced its battery capabilities from having just 8 batteries to now having 12 batteries. This ensures that even in case of a complete loss of an alternator, we still have the stored power adequate to make sure that the vehicle can pull over safely, send out distress signals to make sure that it is rescued.
Quick follow-up on the batteries too, right? And just as a point of clarification, because the question can come up when we're talking about autonomous, and you got more batteries there, you got some of those orange cables that we're all becoming familiar with now with battery electric powertrain trucks, right? But this is still very much diesel world, diesel autonomous trucks. It's not an electric truck, it's not an electric truck system, it's just additional power that you need for those redundant systems and other demands, right? This is still very much in the diesel world.
That is correct. The propulsion system is still a traditional internal combustion engine. It's a diesel engine. Under the hood, you would see a Detroit diesel engine, and the transmission is Detroit transmission. So under the hood, it is a very traditional, very familiar, and very successful Detroit powertrain that propels this vehicle. The systems that we have developed enhances the capability of a self-driving system commanding this vehicle safely and reliably. The cables that you see here, the red cables and the black cables are all familiar to the industry. The 48-volt generator is the one that would have the blue cable, indicating that it is at 48 volts. Other than that, it is a very familiar architecture when it comes to low-voltage systems. We have designed the braking system, the steering, and all the elements of a self-driving system agnostic to what propels the vehicle, which means that when we have an electric Cascadia, we will be able to make that also an autonomous electric Cascadia because the fundamentals of what makes a vehicle redundant is still the same. Even an electric Cascadia would require redundancy when it comes to braking systems and steering system. The only difference is going to be what propels the vehicle and what provides the electrical requirements of all the controllers. A couple of questions that always comes up. If you zoom out and look at the cab, this is a 72-inch sleeper, the largest and the most spacious cab that's out there in the market. One might ask, why do we need such large and the most spacious cab for a vehicle that is being designed to not having a driver inside? Well, the simple answer to that is currently we are making sure that we have adequate room for our equipment, our test engineers. Soon you will see this morph into something that is more specific for a driverless operation. And until then, you would see this large of a cab. And in case you're wondering, it is because we want to have adequate room for our equipment, for example, data acquisition equipment and our computers, and also make sure that we have enough room for our engineers and our safety drivers. We are currently testing these vehicles, and they're being tested in different parts of the country, some in the southern part of Texas, some in New Mexico area, and some in some test tracks all over. And all these trucks are safely tested with one highly trained safety driver and a safety monitor. This ensures that at no point of time we have any road users or any track users subject to any kind of danger during testing. So it's still a development in progress. We want to make sure that we test in a safe way. So currently you will have these trucks being tested and monitored by not just a highly trained safety driver, but also a safety monitor.
So, and correct me if I'm wrong here, but the idea of that as these trucks roll into applications too, you're still going to need a driver in it, maybe in some instances of getting to routes that you can run on autonomous mode, and going back to the idea of stepping stones for rollouts, right? It's not that the truck just rolls off by itself and shows up by itself. Like, that's the dream. We will get there. That's where we're going. But to roll it out, you're still going to need a driver in there. Maybe behind the, let's say from if you're at a depot, then you're getting to the highway or that kind of thing. Are you looking at a stepping stone rollout where I enable autonomous mode, much like I do adaptive cruise and Detroit Assurance now?
It is important to acknowledge that when we are designing a self-driving system, we design it for a boundary. We refer to it as operational design domain. You will hear this term used in this industry quite a bit. Operational design domain, or ODD, refers to the boundary conditions around which this truck can operate autonomously in a level 4 autonomous mode, which means no driver required behind the wheels. For example, these operational design domains could be geographical, meaning certain corridors are approved and they have been mapped and they've been prepared so that it can operate in an autonomous mode. And outside of those, it still requires a human-driven intervention to make sure it can be operated safely. Right. So think about it as a boundary that we are drawing. Some of them could be geographic. Some of them could be operational conditions and limitations, such as bad weather, such as complication in traffic. Outside of those boundaries, it still will be ready to be operated as a manual-driven truck. Within those boundaries, within those geographic conditions and operational design domain, it is being built so that it can operate without a human driver. And as you know, in addition to enhancing highway safety, which is our primary goal, every year we lose about 5,000 lives due to accidents resulted from Class 8 trucks. Someday that number needs to come down to 0. And we know that autonomous has the capability of operating these vehicles safely and reliably. In addition to that, we also know the demand for moving freight keeps increasing year after year, and that is currently not being met by enough drivers coming in and supporting that. So our goal is not only to enhance highway safety with the help of autonomous solutions, but also to provide freight efficiency solutions so that we can enable our customers to get the maximum value from not only a human-driven Cascadia, but also an autonomous Cascadia.
Right, right. I mean, one of the things that I always find fascinating when we talk about this too is, I mean, you gave the sad statistic there of the number of lives lost. And, as people and people that drive with other people that are driving, I mean, that happens, and it seems that it's easier to forgive a human more than it is to forgive the system, right? The system you're developing is held to a higher standard than a fallible person that I can relate to and empathize with would be, right? So being able to prove that, show that on the road, make people comfortable with the idea that there's the truck and trailer going down the road without anyone behind the wheel, and it's very, very safe. It's perhaps safer than, it's the safest that you're going to be able to design for.
Absolutely. I think one of the things that we want to acknowledge is that the autonomous solution aims at being as good as a human who is at his or her most attentive and his or her best state of mind, his or her ability to provide the best capabilities of controlling the vehicle safely and reliably. What autonomy brings is that always.
Right.
And it is not going to be tired. It is not going to become irritated. It is not going to become something that we cannot rely on. However, there is a lot of responsibility that lies on the shoulders of not just us as a technology originator or an original equipment manufacturer, but also those who operate these vehicles and those who test, those who release these vehicles and service these vehicles. So it is a collective responsibility to develop autonomous solutions. We should never forget the goal, what we are trying to achieve here. We want to achieve highway safety, and we want to achieve freight efficiency. We want to make sure that we cut no corners while doing this exact endeavor.
Well, Suman, I appreciate you taking the time to get me more familiar with the chassis. This was wonderful. I learned a ton. It was great to see you. Thanks for taking the time. I'm sure we'll talk soon as more rolls out in the autonomous world.
Thank you very much. Really appreciate the opportunity.